Now, in this lecture, we'll find the radius of the small circle. In the drawing, we have a circle inside a semicircle. We know that side CD equals to 3 units, so line segment CD equals to 3 units, line segment DB equals to 4 units. And we also know that angle CDB, this angle equals to 90 degrees. And we want to find out the radius, the length of the radius of this small circle. So first of all, we'll do a construction. We will complete the semicircle to a circle. So we completed this semicircle to a circle. The next step, we will extend line segment CD by a straight line until it touches the circle. And we will define the touching point of the extended line segment CD in the circle as point E. Point E is the touching point of the extended line segment CD and this circle. Okay, so actually we extended the straight line CD by a straight line, and when you extend a straight line by a straight line, the result must be a straight line. That is to say, CE is a straight line. Okay, so I write it down that line segment CE is a straight line. Okay, line segment CE is a straight line, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles here must be equal to 180 degrees. So which angles we have at this side of CE at point D? We have here 90 degrees plus angle EDB. So at point D, we have one angle that is a right angle, it is equal to 90 degrees, and the second angle is angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Here we will subtract 90 degrees from this equation, and we get that the missing angle, angle EDB, is equal to 180 degrees minus 90 degrees, it is 90 degrees. Okay, so we found out that the missing angle is a right angle, it equals to 90 degrees. So here, this is a right angle, angle EDB. So actually, when we did the construction and created a circle from this semicircle, the second semicircle that we created, it is actually a mirror image of the original semicircle. I repeat again, the second semicircle that we created by the construction, it is a mirror image of the original semicircle, this semicircle. Okay, and also after we extended the straight line CD by straight line and created line segment DE, DE is also a mirror image of CD. I repeat again, DE is a mirror image of CD because of the fact that those two angles above, they are both equal to 90 degrees. And the two semicircles are mirror image, this semicircle is mirror image of the original semicircle. Therefore, DE is also a mirror image of CD. And because of the fact that DE is a mirror image of CD, that is to say, it means that CD equals to DE. CD equals to DE by symmetry. This is exactly the same thing that when you look at a mirror, you see yourself exactly in the same dimensions that you are in reality, but in the opposite sides. Okay? That is to say, DE equals to CD in its length, but it is in the opposite side. What is really important here is that CD equals to DE, because of the fact that DE is a mirror image of CD. And always the mirror image equals to, in its length, to the image itself. For that reason, DE equals to CD. Okay? But it is given us the question that CD equals to 3 units. So we can write here that CD equals to 3 units. And from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Okay, DE is also equals to 3 units. So we can write here that DE equals to 3 units. In the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, I repeat again on rule number 1, if two chords intersect with each other inside the circle, then the following equation is true. So we actually have, this is called AB, this is called AB, and chord AB intersects with chord CD, this is chord CD. So here chord AB intersects with chord CD is point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 1, AO times OB equals to CO times OD. I'll repeat again. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Okay? So we actually can implement rule number 1 in our drawing, because in our drawing we have this circle, and inside the big circle we have chord AB. This is chord AB that intersects with this chord CE at point D. So I write it down. In our original drawing we have chord AB intersects with chord CE at point D. I'll repeat again. In our original drawing, chord AB intersects with chord CD at point D. Okay? Here, chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, the following equation is true, that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. AD times DB equals to CD times DE. This is true according to rule number 1. AD times DB equals to CE equals to CD times DE. Okay? If AD is the missing line segment, so we will leave it as it is. It is AD times dB. According to what is given as the question, dB equals to 4 units, so we'll substitute dB by 4. And it is equal to CD. It is given as the question that CD equals to 3 units, so we substitute CD by 3 times DE. We have already found out that DE is also equal to 3 units. So in conclusion, we found out that according to rule number 1, AD times 4 equals to 3 times 3. 3 times 3 is 9, and 9 equals to 4 AD according to rule number 1. So here we will divide this equation by 4, and we get that AD, the missing line segment AD, equals to 9 over 4 units. So here we can write down in the drawing The drawing that AD equals to 9/4 units. Okay, we actually know that AB is the diameter of this big circle and also the diameter of the semicircles. And we also know that the diameter of any circle is twice as long as the radius. So if we divide the diameter AB into 2, we get the radius. So we will define the radius of this big circle as capital R. This is also the radius of the semicircles. And capital R, it is equal to the diameter AB over 2. Okay? And here the diameter AB is equal to AD plus DB. Again, the diameter AB equals to AD plus DB. So we substitute AB by AD plus DB and we divide it by 2, and in this way we get the radius of the big circle, that is also the radius of the semicircles. But we have already found out that AD equals to 9/4, so we substitute AD by 9/4, and we have already found out that DB equals to, it is given us the question that DB equals to 4 units, so we substitute DB by 4, all divided by 2. So here we will multiply 4 by 4 and then we will divide it by 4 in order to have a common factor with 9/4. So 4 times 4 is 16, so in the numerator we have 9 plus 16 over 4 divided by 2. 9 plus 16 is 25 divided by 4 over 2. We'll move 2 to the denominator and we get that the radius of the big circle equals to 25 over 4 times 2. 4 times 2 is 8, so it is the radius of the big circle equals to 25 over 8 units. So I write it down here that the radius of the big circle, that is also the radius of the semicircles, it is equal to 25 over 8 units. Okay? In the next step, we will define the center of the big circle SP. This is the center of the big circle. So the center of the big circle is at point P, and we will define the center of the small circle as point Q. Okay? So what is the length of the short line segment DP? From the drawing, it is very easy to see that the length of line segment DP, it is equal to DB minus PB. DB minus PB. I repeat again, the length of the short line segment DP equals to DB minus PB. It is very easy to see it from the drawing. So DP equals to DB. It is given us the question that DB equals to 4 units, so we'll substitute DB by 4 minus PB. What is the length of line segment PB? P is the center of the big circle. B is the point of the big circle itself. And that is exactly the definition of a radius. So PB equals to capital R, that is the radius of the big circle. So in conclusion, we found out that dP equals to 4 minus capital R. But we have already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We do it now, and we get that dP equals to 4 minus capital R, that is 25 over 8. So here we will multiply 4 by 8, and then we divide it by 8 in order to have a common factor of 25 over 8. So we get here that dP equals to 4 times 8 is 32, minus 25 over 8. 32 minus 25 is 7. So in conclusion, we found out that dP equals to 7/8. Okay, dP equals to 7/8. dP equals to 7/8. So we can write here that the length of the short line segment dP is equal to 7/8. Okay, so in the next step, we will define the point of tendency of tangent dB with this small circle as point M, and we will define the point of tendency of tangent CD with this small circle as point O. And from point Q, we will draw the radius to point O. Okay? So here we will have the radius QO that is drawn to the point of tendency. That is to say, the radius QO of the small circle, it is drawn to point O, that is the point of tendency of tangent DC with this small circle. Here I'll repeat again why QO is the radius of the small circle. QO is the radius of the small circle because of the fact that line segment QO starts from point Q, that is the center of the small circle, and ends at point O, that is a point on the small circle itself. And this is exactly the definition of a radius. So we define the radius of the small circle as R, small r. So QO is the radius of the small circle that is equal to small r, and here the radius of the small circle QO, it is drawn to the point of tendency, that is to say, it is drawn to point O, that is the point of tendency of tangent CD with this small circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius MQ. The tangent CD will be perpendicular to the radius OQ. So CD is perpendicular to OQ, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? Likewise, from point Q, we will draw the radius to point M. QM is the radius of the small circle that is equal to small r, because of the fact that QM, line segment QM, starts from point Q, that is the center of the small circle, and ends at point M, that is a point on the small circle itself. This is exactly the definition of a radius. Therefore, QM is the radius of the small circle that is equal to small r. Okay, and then here we have the radius QM that is drawn to the point of tendency, That is to say, the radius QM, it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So DB is perpendicular to MQ. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees. I repeat again, whenever we have a radius that is drawn to the point of tendency, like here, the radius QM, it is drawn to point M, that is the point of tendency of tangent DB with this small circle, then the tangent DB will be perpendicular to the radius MQ. If DB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So we will focus on quadrilateral OQDM, this quadrilateral. In quadrilateral OQDM, we have 1, 2, 3 right angles. So I write it down. In quadrilateral OQDM, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle, that is actually angle OQM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here, 270 degrees plus the size angle of angle OQM. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here, we will subtract 270 degrees from this equation. And we will get that the missing angle OQM is equal to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that the missing angle, it is a right angle, it is equal to 90 degrees. So if this angle OQM, it is a right angle. So actually, in quadrilateral OQDM, we have 4 right angles. And because of the fact that in quadrilateral OQDM we have 4 right angles, it means that quadrilateral OQDM must be at least a rectangle. So we'll relate to quadrilateral OQDM as a rectangle. So I'll write it down. Quadrilateral OQDM is a rectangle. Okay, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle OQDM, OQ must be equal to DM. OQ must be equal to DM, according to the rule that the opposite sides of a rectangle are equal to each other. But we know that OQ equals to small r, it is the radius of the small circle. OQ equals to small r, and from this equation r equals to OQ equals to dm, we will derive that dm is also equals to small r. dm equals to small r, this is the radius of the small circle. Here dm equals to small r. Okay, and what is the length of line segment PM? From the drawing, it is very easy to see that the length of line segment PM here PM equals to DM minus DP. I will repeat again. The length of line segment PM equals to DM minus DP. And we know that DM equals to small r, so we'll substitute DM by small r. And we have already found out that dp equals to 7/8. So we substitute dp by 7/8. So in conclusion, we found out that pm equals to small r minus 7/8. Here, pm equals to small r minus 7/8. So we can write here that pm equals to small r minus 7/8. Okay. In the next step, I will present to you a new rule that is actually rule number 2. But first of all, we will define this point as point S. Point S, it is actually the launch point of the small circle with the big circle. So I write it down. It is the launch point of the big circle with the small circle. That is to say, at point S, the big circle touches the small circle. It is the touching point of the big circle with the small circle, or also you can define it as point of tendency. And because of the fact that those two, the small circle is located inside the big circle, it is defined as internal lunge. That is to say, those two circles, they are touching each other internally at point S. Point S is the launch point of the big circle with the small circle. Okay, so in this drawing we have an internal lunge between the big circle and the small circle. They are touching each other internally at point S. Okay, I repeat again that because of the fact that the small circle is located inside the big circle, this touching point is defined as an internal lunge. Okay, so in this circle we have an internal lunge between the big circle and the small circle at point S. Point S is the lunge point. Okay, so now I will present to you rule number 2. According to rule number 2, if two circles have an internal lunge between them, like in our drawing, those two circles have an internal lunge between them at point S. This is rule number 2. So if two circles have an internal lunge between them, then the straight line that connects the two centers together, the straight line that connects their centers. Passes through the launch point. So I'll read rule number 2 again. According to rule number 2, if two circles have an internal launch between them, then the straight line that connects their centers passes through the launch point. So in our original drawing, we have here an internal launch at point S, and according to rule number 2, here point P is the center of the big circle, point Q is the center of the small circle, and the line segment PQ is the straight line that connects the two centers together. Here, the red line segment PQ is the straight line that connects the two centers together, and according to rule number 2, this straight line passes through the launch point. Point S is the launch point, so the straight line PQ passes through point S. That is to say, here PQS is one straight line. Okay, so according to rule number 2, the 3 points P, Q, and S, they are all located on the same straight line. So you can conclude from rule number 2 that points P, Q, and S are located on the same straight line. Okay? Or in other words, line segment PQS is a straight line. Line segment PQS is a straight line. This is true according to rule number 2, of course. So, what is the definition of line segment QS? Q is the center of the small circle. S is the point of the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. Okay? And what is the definition of line segment PS? The definition of line segment PS: P is the center of the big circle. S is a point on the big circle itself. This is exactly the definition of a radius. That is to say, PS is the radius of the big circle that is equal to capital R. But we have already found out that capital R equals to 25 over 8, so actually PS equals to 25 over 8 units. It is the radius of the big circle that is equal to 25 over 8 units. And what is the length of PQ? From the drawing, it is very easy to see that the length of line segment PQ here PQ equals to PS minus QS. I'll repeat again, PQ equals to PS minus QS. Okay? Here PQ equals to PS minus QS. So PQ equals to PS. PS, we already found out that PX equals to capital R, so we substitute PS by capital R minus QS. We already found out that QS equals to small r. So in conclusion, we found out that PQ equals to capital R minus small r. But we have already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We'll do it now, and we get that PQ, in conclusion, PQ equals to 25 over 8 minus small r. Okay, PQ equals to 25 over 8 minus small r. So here, PQ equals to 25 over 8 minus small r. In the next step, we will focus on the green right triangle QPM. I'll copy the right green triangle QPM in a new page, and we will implement the Pythagoras theorem on this right green triangle QPM. As you can see from the drawing, the only missing variable in this triangle is small r, and we'll find out the value of small r by implementing the Pythagoras theorem on this green right triangle QPM. Okay, so I'll copy the right triangle QPM in a new page. So actually, this is the right triangle QPM that I copied from the original drawing, and we have already found out that the radius PQ equals to the hypotenuse PQ of this right triangle PQM equals to 25 over 8 minus small r. We have already found out that side PM of this right triangle equals to small r minus 7/8, and we have already found out that QM equals to small r, it is the radius of the small circle. So in the right triangle QPM, by PT is a relation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars according to the Pythagoras theorem. The hypotenuse in this right triangle PQM is PQ, therefore the square of the hypotenuse is PQ square, and it is equal to the sum of the squares of the perpendiculars, that is to say, it is equal to QM square plus PM square. Okay, so here PQ equals to 25/8 minus small r. Therefore, PQ square equals to 25/8 minus small r square, and it is equals to QM square. QM equals to small r, so QM square equals to small r square plus PM square. PM equals to r minus 7/8, therefore PM square will be equal to r minus 7/8 square. Here we will open the brackets on both sides of this equation, equation number 1, and we get that according to equation number 1, 25/8 minus r square, we'll find out the value of 25/8 minus r square according to the algebraic identity that states that a minus b square equals to a square plus b square minus 2 times ab. So if 25/8 minus r square will be equal to 25/8 square, that is 25 square is 625 over 8 square, that is 64, plus r square minus 2 times 25/8 times r. And it is equal to r square plus r minus 7/8 square. R minus 7/8 square equals to r square plus 7/8 square. 7/8 square is 7 square is 49 over 8 square is 64 minus 2 times r times 7/8. Okay. So here we have r square on both sides of the equation, so r square will get cancelled. What is left from equation number 1 after we cancelled r square? What is left? It is actually here we have 625/64. And here we have 2 times 25r/8. Here we divide both the numerator and the denominator of this expression by 2, and we get that minus 2/2 is minus 1, so 2 will get cancelled. In the numerator we left only with minus 25r. In the denominator we have 8, so 8 is divided by 2, it is equal to 4. So in conclusion, this expression equals to minus 25r over 4. On the other side of the equation we have r square plus 49/64 minus 2 times r times 7/8. Here we will divide both the numerator and the denominator of this expression by 2. Minus 2/2 is minus 1, so in the numerator we have in total minus 7r. In the denominator we have 8 that is divided by 2 is equal to 4. So in conclusion, this expression equals to minus 7r over 4. Here we will multiply this equation by 64, and we will get that according to equation number 1, (625) times 64 over 64, it is equal to 625. And here we have to multiply by 64 this expression, so it is actually minus 64 over 4 is minus 16. And we have also here 25r. So in conclusion, this expression, after we multiply it by 64, equals to minus 16 times 25r. And it is equal to r squared times 64 is equal to 64r squared. 49 times 64 over 64 equals to 49. Here we have 64 minus 64 over 4 is minus 16. And we have to multiply it also by 7r. So in conclusion, this expression, after we multiply it by 64, equals to 16 minus 16 times 7r. Okay? So here, according to equation number 1, $625 minus 16 times 25r equals to minus 400r, and it is equal to 64r squared plus 49, and minus 16 times 7r is minus 112r. So here we will add minus 400r to this equation, equation number 1. We will add 400r to this equation, equation number 1. And we will get here that 625, 400r minus 400r is 0. So once 400r will get cancelled. So in this side of the equation, we left only with 625, that is equal to 64r squared plus 49, and here we have 400r minus 112r, it is equal to plus 288r. Okay? Here we will subtract 625 from this equation, equation number 1, and we will get that according to equation number 1, 625 minus 625 is 0, and it is equal to 64r squared plus 288r, and 49 minus 625 equals to minus 576. So we have here a quadratic equation. We divide this quadratic equation by 32, and we get that according to equation number 1, 64r squared over 32 equals to 32r squared, 288r over 32 equals to 9r, and minus 576 over 32 equals to minus 18, and 0 over 32 equals to 0. So in conclusion, we got the quadratic equation that 30 is actually here 64 over 32 is 2, so here we left only with 2r squared, because 64 over 32 is 2, so this expression equals to 2r squared in total. Okay, so in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient A equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 18. And the variable that we are looking for in this quadratic equation is r, so x equals to r. And the general formula for solving out a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Okay, here a, b, and c are the coefficient of the quadratic equation, and x is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is r, so we substitute x by r, and r equals to minus b equals to 9, so minus b is minus 9, plus minus square root of b squared, b equals to 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c is minus 18. All divided by 2a, a is 2, so 2 times 2 is 4. So actually found out that r, the radius of the small circle, it is equal to minus 9 plus minus square root of 81 minus 2 times minus 4 times 2 is minus 8, and minus 8 times minus 16 is plus 144. So inside the root we left only with 81 plus 144, all divided by 4. So here r equals to minus 9 plus minus 81 plus 144 is 225. So inside the root we left only with 225 divided by 4. So here r, the radius of the small circle, equals to minus 9 plus minus the square root of 225 is 15 over 4, so here we will have two solutions that are possible for r, the radius of the small circle. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So I actually found out that r equals to minus 6, but because of the fact that r is the length of the radius of the small circle, r is a length, it must be a positive number. So I write it here, that r is a length, and as a length it must be a positive number, so it can never be equal to minus 6, that it is a negative number, so we'll cancel the solution, and we'll focus on the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, so r equals to 6 over 4. Here we divide both the numerator and the denominator of this side of the equation by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r, the radius of the small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. I repeat again. R, the radius of this small circle, it is equal to either 3/2, or in terms of numbers, it is equal to 1.5 units. In the next step, I will summarize the lecture. Actually, we wanted to find out the radius of the small circle that is inside the semicircle. We know that side CD equals to 3 units, side DB equals to 4 units, angle CDB equals to 90 degrees, and we want to find out the radius of this small circle that is inscribed by a semicircle. Okay? So first of all, we did the construction. We completed the semicircle to a circle, and in this way we created 2 semicircles. The new semicircle that we created is the mirror image of the original semicircle. Okay? And then we extended the straight line CD by straight line, and we defined the touching point of the extended straight line CD in the circle as point E. Okay? So because of the fact that we extended the straight line CD by straight line, the result must be a straight line. That is to say, CE must be a straight line. When you extend a straight line by straight line, the result must be a straight line. That is to say, CE is a straight line. This line segment CE is a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line C at point D, then the sum of the angles here must be equal to 180 degrees. So here at point D, on this side of the straight line CE, which angles we have? Here we have 90 degrees, and then get EDB. So 90 degrees plus angle EDB in total must be equal to 180 degrees, according to the rule that I mentioned. Here we subtracted 90 degrees from this equation and found out that the missing angle EDB, this angle equals to 90 degrees. So angle EDB equals to 90 degrees, and angle CDB is also equal to 90 degrees. And because of the fact that those two angles are both equal to 90 degrees, actually DE is the mirror image of CD. And because of the fact that DE is the mirror image of CD, DE must be equal to CD. Why? Because when you look at yourself in a mirror, when you look on yourself in a mirror, you see yourself exactly in the same dimensions, but in the opposite side. Therefore, here it is also the same thing. DE is the mirror image of CD, therefore the length of DE must be equal to CD. But the only difference between those two line segments CD and DE and their direction. They are not in the same direction, but in the opposite side. So in conclusion, because of the fact that DE is the mirror image of CD, it must be equal to CD in its length. And the only difference between them is their direction is one is opposite to other. That is to say, DE is equal to CD by symmetry, because DE is the mirror image of CD. Okay? But it is given us the question that CD equals to 3 units. Here, CD equals to 3 units, according to what is given us the question. And from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Here, DE is also equals to 3 units. Okay? In the next step, I presented to you rule number 1, according to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true, that AO times OB equals to CO times OD. So here we have this circle. Inside this circle we have chord AB. Chord AB intersects with chord CD. The red chord, it's point O. Point O is the intersection point of chord AB with chord CD. Okay? And if this is the data that has been given to us, then according to rule number 1, we will get that the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, so we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have chord AB, we have this circle. Inside this circle we have chord AB that intersects with chord CE at point D. Again, chord AB intersects with chord CE at point D. I'll repeat again. Now our original drawing, chord AB intersects with chord CD at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we will get that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. AD times DB equals to CD times DE, according to rule number 1. AD is the missing line segment, so we will leave it as it is. DB equals to 4 units, according to what is given as the question. CD equals to 3 units, according to what is given as the question, and we already found out that DE is also equals to 4 units. So in conclusion, we found out that according to equation number 1, 4 times AD equals to 3 times 3. 3 times 3 is 9, so in conclusion we found out that 4 times AD equals to 9. We divided this equation by 4, and we found out the missing line segment, that the missing line segment AD is equal to 9 over 4 units. The line segment D equals to 9 over 4 units. Okay? And we actually know that AB is the diameter of this circle and also the diameter of the semicircles. And the diameter of any circle or semicircle is twice as long as the radius. So here, the diameter AB is twice as long as the radius. We define the radius of the big circle as capital R. So if we divide the diameter AB by 2, we get the radius capital R. So the radius that is defined as capital R, it is equal to the diameter AB over 2. Okay? Here AB, according to the drawing, AB equals to AD plus DB. We substitute AB by AD plus DB. AD equals to 9 over 4, according to what we have already found out. DB equals to 4 units, according to what is given as the question. And all divided by 2. Here we multiply 4 by 4 and we divide it by 4 in order to have a common factor with 9 over 4. So 4 times 4 is 16, and 16 plus 9 is 25, all divided by 4 and all divided also by 2. So we moved 2 to the denominator, and we found out that the radius of the big circle equals to 25 over 4 times 2. 4 times 2 is 8. So in conclusion, we found out that the radius of the big circle equals to 25 over 8 units. Okay? Here the radius of this big circle equals to 25 over 8 units. Then we found out the length of the short line segment DP. Here, what is the length of this line segment DP? The length of line segment DP from the drawings is very easy to see that the length of this line segment DP is equal to DB minus PB. Okay, DB minus PB equals to DP. Here, DP equals to DB minus PB. Okay. So it is given as the question that dB equals to 4 units. So we substitute dB by 4. P is the center of the big circle. B is the point of the big circle itself. This is exactly the definition of a radius. That is to say, PB is the radius of the big circle that is equal to capital R. Okay? So PB equals to capital R. So in conclusion, we found out that the length of the small line segment dP is equal to 4 minus capital R. But we already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We did it when we got that dP equals to 4 minus 25 over 8 units. And here we multiplied 4 by 8 and then we divided by 8 in order to have a common factor with 25 over 8. So 4 times 8 is 32 minus 25 over 8. 32 minus 25 is 7. So dP in conclusion is equal to 7/8. dP, the small line segment dP equals to 7/8. So we can write here that dP equals to 7/8. Then we defined the center of the big circle as point P, and we define the center of this small circle as point Q. And from point Q, here we know that the point of tendency of tangent CD with this small circle is at point O, and here the point of tendency of tangent DB with this small circle is at point M. So, first of all, from the center of the small circle, that is to say from point Q, we draw radius to point O, that is the point of tendency of tangent CD with this small circle. So here we have the radius of the small circle that is equal to small r according to our definition. Here the radius QO, it is drawn to the point of tendency. That is to say the radius QO, it is drawn to point O, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to that radius. Again, CD is perpendicular to the radius OQ. That is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, likewise from point Q, we draw the radius QM of the small circle to point M. So we draw the radius to point M, that is the point of tendency. And whenever a radius is drawn to the point of tendency, like in this case, then the tangent dB will be perpendicular to the radius MQ. Again, dB is perpendicular to MQ. That is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so if we focus on quadrilateral OQDM, in this quadrilateral we have 1, 2, 3 right angles. Okay, in quadrilateral OQDM we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle, that is actually angle OQM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation, and we found out that angle OQM, the missing angle, it is equal to 360 degrees minus 270 degrees, that is 90 degrees. So if the missing angle OQM equals to 90 degrees. Therefore, actually in quadrilateral OQDM, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So in rectangle OQDM, OQ must be equal to DM. OQ must be equal to DM. We have already found out that OQ equals to small r. So you can write here that OQ equals to small r, and from this equation I equals to OQ equals to dm, we will derive that dm is also equals to small r. Here dm equals to small r. Okay? And what is the length of line segment PM? The length of line segment PM, from the drawing it is very easy to see that PM equals to dm minus dp. Again, dm minus dp equals to PM. Here, this is the letter M. And this is line segment PM. From the drawing it is very easy to see that PM equals to dm minus dp. Okay? PM equals to dm minus dp. dm equals to small r. Here we just write down further that dm equals to small r. We have already found out that dp equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. Here, PM equals to small r minus 7/8. Okay? In the next, actually, here we define the touching point of those two circles, the small circle with the big circle is point S. Point S is the launch point of those two circles, that is to say, it is the touching point of those two circles. Because of the fact that the small circle is located inside the big circle, this type of tangency is defined as internal launch. So in this drawing, we have an internal launch between the big circle and the small circle. Point S is the launch point of those two circles, the big circle with the small circle. And in this drawing, we have an internal launch between the big circle and the small circle. That is to say that those two circles are touching each other internally at point S. Okay? Then I presented to you rule number 2. According to rule number 2, if two circles have an internal launch between them, then the straight line that connects their centers passes through the launch point of the two circles. Okay? So here, as I already mentioned, we have in this drawing an internal launch between those two circles, the big circle and the small circle. And according to rule number 2, this rule, here, point P is the center of the big circle, point Q is the center of the small circle. Therefore, line segment PQ that connects their centers, that is of course a straight line, must pass through point S, that is the launch point between those two circles. Okay? The straight line PQ that connects the two centers together must pass through point S, that is the launch point between those two circles. That is to say, points P, Q, and S, all of them, they are located on the same straight line. Okay? We can derive from rule number 2 that points P, Q, and S, they are located all on the same straight line. Or, in other words, PQS is one straight line. According to rule number 2, here PQS is one straight line. According to rule number 2, of course. And here, what is the length of line segment QS? Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. Very simple. What is the definition of line segment PS. P is the center of the big circle. S is the point on the big circle itself. This is exactly the definition of a radius. That is to say, PS is the radius of the big circle that is equal to capital R according to our definition. But we have already found out that capital R equals to 25/8, so PS actually equals to 25/8 units. The length of PS is 25/8 units. And what is the length of line segment PQ? From the drawing, it is very easy to see that the length of this line segment PQ, it is equal to PS minus QS. Here, PQ equals to PS minus QS. We have already found out that PS equals to capital R. So we can substitute PS by capital R. We have already found out that QS equals to small r. So we can substitute QS by small r. So in conclusion, we found out that the length of line segment PQ equals to capital R minus small r. But we have already found out that capital R equals to 25/8, so we can substitute capital R by 25/8. We did it, and we got in conclusion that PQ equals to 25/8 minus capital R. Here, this line segment PQ equals to 25/8 minus small r. Okay? And we already found out that PM equals to small r minus 7/8, and QM equals to small r. So, in the green right triangle, we will implement the Pythagoras theorem. By implementing the Pythagoras theorem on the green right triangle QPM, we will find out the only variable that is missing, that is small r. That is the variable that we are looking for in this lecture. That is the radius of the small circle. Okay? So I copied the right triangle QPM in this new page. We know that PQ, the hypotenuse equals to 25/8 minus small r, PM equals to small r minus 7/8, and QM equals to small r. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in the right triangle QPM. The hypotenuse is PQ, so the square of the hypotenuse is PQ square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to QM square plus PM square. PQ equals to 25/8 minus r, so PQ square will be equal to 25/8 minus r square. QM equals to r, so QM square it is r square, plus PM square. PM equals to r minus 7/8, so PM square equals to r minus 7/8 square. Here we open the brackets on both sides of the equation. 25/8 minus r square, it is equal to 25/8 square. That is 25 square is 625/8 square is 64. Plus r square, minus 2 times 25/8 minus r. And in the other side of the equation we have r square plus r minus 7/8. R square plus r minus 7/8 square. We open the brackets here. It is equal r minus 7/8 square equals to r square plus 7 square over 8 square, that is 49/64, minus 2 times r times 7/8. Here we have r square on both sides of the equation, so r square will get cancelled, and we left only 625/64. And here we have also this expression, 2 times 25r over 8. We divided both the numerator and the denominator of this expression by 2. So 2 over 2 is 1. So this expression in the numerator we have left only with minus 25r. In the denominator we have 8 that is divided by 2 is 4. So here we have r square. So r square will get cancelled because we have r square on both sides of the equation, but we have another r square also, plus 49/64 minus 2 times r times 7/8. Here we divided both the numerator and the denominator of this expression by 2. 2 over 2 is 1, so this expression equals, in the numerator we have left only with minus 7r, In the denominator we have 8 that is divided by 2, it is equal to 4. We multiply this equation number 1 by 64. 625 times 64 over 64 is 625. Here we have minus 25 r over 4 times 64. It is actually minus 64 over 4, that is minus 16, and it also multiplied by 25r. So this expression, after we multiply it by 64, it is equal in total to 16 times 25r, and we have here r squared times 64 is 64r squared. 49 times 64 over 64 is 49, and here we have minus 7r over 4 times 64, it is actually minus 64 over 4, that is minus 16 times 7r. So this expression in total, it is equal to minus 16 times 7r. After we multiply it by 64, it is equal to minus 16 times 7r. Okay? So here, 16 times 25r is 400r, and there minus 16 times 7r is minus 112r. So in conclusion, according to equation number 1, we found out that 625 minus 400r equals to 64r squared plus 49 minus 112r. We added 400r to this equation number 1, and found out that here we have 625. 400r minus 400r is 0. So in this side of the equation number 1, we left only with 625. In the other side of the equation, we have 64r squared minus plus 49. And here we have 400r minus 112r, it is plus 288r. So in conclusion, we found out that according to equation number 1, 625 equals to 64r squared plus 49 plus 288r. We subtracted 625 from this equation number 1, and we found out that 625 minus 625 is 0. Here we have 64r squared plus 288r, and 49 minus 625 equals to minus 576. So in conclusion, we found out that according to equation number 1, we got the quadratic equation that 0 equals to 64r squared plus 288r minus 576. Here we divided this quadratic equation by 32, and we got that 64 over 32 is 2. So this expression in total equals to 2r squared. 288r minus 30 over 32 is 9r, and minus 576 over 32 equals to minus 18. So in conclusion, we found out that according to equation number 1, 2r squared plus 9r minus 18 equals to 0. So we got this quadratic equation. The coefficient A in this quadratic equation is 2, the coefficient B in this quadratic equation is 9, and the coefficient C in this quadratic equation is minus 18. And the variable that we are looking for in this quadratic equation is r. So x equals to r. And the general formula to solve out a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Here a, b, c are the coefficients of the quadratic equation, and x is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is r, so x equals to r, so we substituted x by r, and we found out that r equals to minus b, b equals to 9, so minus b is minus 9, plus minus square root of b squared. B is 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, and c is minus 18. So this expression equals minus 4 times ac equals to minus 4 times 2 times minus 18. All divided by 2a. A is 2, so 2a is 2 times 2, that is 4. So here r equals to minus 2 plus minus 81. And here we have minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. all divided by 4. So here r equals to minus 9 plus minus 81 plus 144 is 225. So inside the root we left only with 225, all divided by 4. So here we got that r, the radius of the small circle, it is equals to minus 9, and the square root of 225 is 15. So here we have two solutions that are possible for r equals to minus 9 plus minus 15 over 4. The first solution for r, the radius of the semicircle, it is equal to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r, the radius of the small circle, equals to minus 6, that is a negative number, but r is the length of the radius of the small circle, and r is a length, it must be a positive number, and because of the fact that r must be a positive number, this solution that r equals to minus 6, that is a negative number, is incorrect solution. We cancel this solution, and we left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4, here r equals to 6 over 4. We divided both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, and 3 and 4 over 2 is 2. So in conclusion, we found out that r, the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. So we repeat it again, r, the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.